Okay, so on Monday, if you remember, we started discussing the density matrix. So the question we are trying to address, or the system that we would like to study, is we had this one example where we have one Stern-Gerlach experiment, let's say, in the z direction, and we send a beam. It will split into two. Let's say we block one of them, we take the other one, and then we have another system. Let's say this time Stern-Gerlach experiment, but this time the magnetic field is aligned in the x direction. Again, we send some beam of silver atoms. This will be split into two, and then we block another one. And then we might mix these. You see, the particles that come from the upper Stern-Gerlach system, we know that they are all in the state minus. That is what we call a pure state. All the particles in the coming from the above Stern-Gerlach experiment, they are described by exactly the same way, ket. Whereas the particles coming from the lower Stern-Gerlach ket system is in the Sx plus state. So again, that is also a pure ensemble, so-called, a pure system. All the particles in the second system, they have a single, they are described by exactly the same ket. But then when we mix them up, the particles in the mixed ensemble, this is a pure ensemble. This is a pure ensemble. When we mix them, the system is now called a mixed ensemble. We cannot talk about a single ket describing all the particles in that system. So our previous three arguments, our previous method framework, let's say, based on describing our system in terms of a single ket will not be applicable in this mixed ensemble. So we just devise new tools. And that density matrix is what is our new tool. So basically, let's say in this mixed ensemble, omega I of them, omega I, a fraction of it, is in the minus state, let's say omega 1, and omega 2 of them will be in the Sx plus ket. Let's say it might be 50%, 50%, 20%, 80%. These omega I, they just tell me the weight of the relevant pure ket. And if in this mixed ensemble we want to calculate some expectation value of some operator, well, when you are taking the expectation value, you are basically measuring this A for every particle and then averaging over your outcomes. Well, omega 1 of them, omega 1 fraction of my particles will be in the minus kets. So when I'm making measurements on these minus kets, my average will be minus A minus. And then omega 2 of them will be in the Sx plus. So if I measure this quantity A in this mixed ensemble, this will be my average. Which, by the way, I can also write as trace of A, omega 1 minus plus omega 2, Sx plus, Sx plus. And it's basically this observation that tells me that I can identify this operator with, let's say, rho, what we call the density matrix. The nice thing about this density matrix is that it is independent of A. So no matter which observation I make, if I know rho, I can calculate the average I will obtain out of that observation. In that sense, it is also similar to my basis ket, my kets. Because if I know the ket of a system, then I know what the averages of my measurements will be. In fact, I know everything about the system. Just like that, if I know rho, I know everything about my system. And in fact, this description in terms of the density matrix also contains our description in terms of kets. So because if we have a pure state, a pure state will be basically for which, let's say, omega 1 is 1, omega I is 0 for all other kets, and the omega 1, let's say, is with 100% probability it's in the state psi, so rho in this case is just psi psi. Sure. That depends on how you prepare your system. You see, you need to kind of, when you are preparing a system, you do it in a particular way, right? So, I mean, and you do it in that way to create a system with particular properties. Those properties are what we call the omega 1, omega 2, etc. Now, if you are given a random system, of course, we don't know what omega 1 and omega 2 are. We know that there are some values, omega i's, but we don't know what they are. We need to measure them. And what we do to measure, usually we make multiple copies if we can. And we measure some of them because measurement basically will destroy the properties of my system. So after measurement, I will not have my initial system, so I should better have copies. I make the copies prepared in identical way. So I make measurements on these copies and try to understand what are the properties of the system that I have created. And out of those measurements, I try to extract what these omega i's are, whether it's a pure state or not. Now, in general, the density matrix will be just the sum of, there will be certain fractions of my system prepared in a particular way. They will be in a particular state. Let's say omega I fraction will be in this ket psi I. So this is what we call the density of states. Density matrix, sorry. This is my density matrix in the general case. Now, one property, if you just take, let's say, the trace of rho, this will be, trace of rho is just, you just pick up an arbitrary basis, let's say bj, rho bj, you look at the diagonal element, sum over the diagonal elements, this is how we define the trace of any operator. This will be equal to sum over j, bj, sum over I, omega I, psi I, bj, which is equal to sum over j, sum over I, let's say, omega I, sum over j, psi I, bj, bj, psi I. But you see, this sum over j is just the identity operator. So this will be sum over I, omega I, psi I. This is just 1 due to our normalization of the states. So trace of rho is just sum over I, omega I, but the sum of all the weights is nothing but 1. Just 1. So this is one property of the density matrix. Its trace has to be 1. This is just equivalent to the sum of the probabilities to be equal to 1. This is our, let's say, in the ket formalism, we were defining the normalization of the ket. This is the normalization of the density matrix. Now we can look at rho squared. You see, rho squared will be sum over I, omega I, psi I, times sum over j, omega j, psi j, which is equal to sum over ij, omega j, psi j, psi j, they are not necessarily orthogonal to each other. So we cannot really simplify any further. Let's take the trace of rho squared. Now, trace of rho squared will be ij, omega I, omega j, psi j, psi I, psi j. This is the trace of rho squared, which is sum over ij, omega I, omega j, the absolute value of psi I, psi j squared. Well, let me make a simplifying assumption. I will just assume that these psi r's are orthogonal. They don't have to be in general, but let's just assume they are orthogonal to each other. That will just simplify my life. Well, if they are orthonormal, then this psi I, psi j inner product is nothing but Kronecker delta ij. Its square is also Kronecker delta ij. So Kronecker delta ij is either 0 or 1. The square of 0 or 1 is itself. So the trace of rho squared is equal to sum over I omega I squared. And keep in mind that omega I is less than or equal to 1. Well, this tells me that omega I squared is always less than or equal to omega I. So this is less than or equal to sum over I omega I, but sum of omega I is nothing but 1. So trace of rho is equal to 1, but trace of rho squared is less than or equal to 1. And trace of rho squared is equal to 1 only if omega I, one of the omega i's is 1, the others are 0. Only if this is satisfied, if this is the case, then omega I squared is always equal to omega I, not less than, it's equal to omega I. And if omega I squared is equal to omega I, sum over omega I is equal to 1. So basically, this is one way of looking at whether a state is a pure state or not. You see, the problem is, let's assume we have a pure state. Rho is equal to Sx plus Sx plus. Well, if rho is diagonal, then it's kind of easy to see that it's a pure state. On the diagonal, only one element will be 1, all the others will be 0. But if it's not diagonal, like this one, see, this is 1 over 2 plus 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 minus minus plus plus minus plus minus plus. Or in matrix form, 1 over 2, 1, 1, 1, 1. Rho is this one. Trace of rho is 1. Let's look at trace of rho squared. Well, you see, the easiest way to see is if rho is this one, rho squared is equal to rho. Well, let's show that rho squared is equal to Sx plus times Sx plus. Well, this is 1. So rho squared is Sx plus, which is nothing but rho. So trace of rho squared is, once you notice this, the trace of rho squared is trace of rho, which is 1. But let's look at our matrix. Trace of rho squared is trace of 1 over 4, 1, 1, 1, 1 times 1, 1, 1, 1. This is trace of 1 over 4, 2, 2, 2, 2. This is trace of 1 over 2, 1 over 2, 1 over 2, 1 over 2. Well, this is nothing but our rho. This is 1. So we know that, if you just look at this rho to start with, it's not easy to say whether it's a pure state or not. To say it is a pure state, you have to diagonalize it, and once you diagonalize it, if you see that on the diagonal, all the diagonal entries except then 1 is 0, then you can say that it's a pure state. But by just looking at the traces, trace of rho should always be 1, whether it's a pure state or not. But if you look at trace of rho squared, if it is 1, then it's a pure state. This is a pure state. So this is just the nice thing about looking at trace of rho squared is also, you see, rho squared, the trace doesn't depend on which basis you use. You see, in this basis of Sz plus Sz minus, rho is not diagonal. So it's not easy to see whether it's a pure state or not. But trace of rho squared, whichever basis you choose, it has the same value. So since trace of rho squared is equal to 1, we already know that there is a basis in which, in the basis in which it is diagonal, only one element is non-zero. Now, of course, so now this is a way of describing our system, the density matrix. But how does it evolve? What about the dynamics? We already know the dynamics of the Schrödinger equation, let's say, for the kets. But what about this density matrix? How can we calculate the evolution of the density matrix? So let's see. Let's assume that at t equal to 0, we create our mixed state, and the corresponding density matrix is this one. Well, this you can just imagine as a collection of as an ensemble of particles, a collection of particles in which some particles are in the psi1 state, some particles are in the psi2 state, some particles in the psi3 state, and their corresponding weights are the weights of their number is omega 1, omega 2, omega 3, etc. Now, if you just let your system evolve on its own, the only thing that will happen will be the particles in the psi1 state will evolve as the ket psi1 evolves, and the particles in the psi2 state will just evolve as a particle in the psi2 state, etc. So their weights will not change, the omega I will not change, but their kets will change with time. So the density matrix at the time t will be nothing but omega I psi I of t, psi I of t. Well, let's look at its time dependence. I h bar del rho by del t. Most of the time it's easier to solve a Schrödinger differential equation than to obtain the wave functions explicitly. Well, the time derivative will be omega I h bar del by del t of this operator I h bar. I can use the chain rule. Well, I know the time derivatives of the kets. Well, the first one is nothing but h psi I of t. And the second one will be minus psi minus h. Now you see the ket is like the complex conjugate, the bra, sorry. And the time evolutions were given these exponentials. But if you take the complex conjugation, the exponentials change their sign. So that's why I have the minus h. So this is h multiplying omega I psi I of t psi I of t minus omega I psi I of t psi I of t multiplying by h from the right. Or I h bar del rho by del t is equal to h rho minus rho times h and rho. It's just a commutator of the Hamiltonian with this rho operator. Well, it looks like the Heisenberg picture. But you see, it's not the Heisenberg picture. The kets are evolving here. Due to the evolution of the kets, the density matrix, density operator in the Heisenberg picture evolves in time. The operators are, the other operators like position and momentum, they are independent of time. This is the Schrödinger picture.
Sadece renklerden aldığı bilgiler anlamında oluyor. Yani state'in kendisiyle de ilgili.
Sure. Yes, this is just a bit of a generalization of the ket. Our descriptions in terms of the kets, they are already encoded in this density matrix. There is this additional information, let's say. Additional flexibility. That not all the particles in our system should be in the same ket. So we can use this density matrix to describe pure states, which before we used the kets to describe them. So we can still use this density matrix to describe such systems. But we can also use rho to describe mixed states, which do not have a single ket. It's just a mixture of various kets. It's not the superposition of various kets. It's a mixture of various kets. You see, a superposition and the mixed state, they are different things. When you are talking about the superposition of various kets, you have a particle, let's say it can be written, let's say, as the superposition of the kets plus and minus. But at the end of the day, that particle has a definite ket. It's just a superposition of different kets. But in these mixed ensembles, you cannot write a single ket to describe all the particles. Some of the particles will be described by one ket, some of them will be described by some other kets. Questions? Well, let's look at something. Let's assume that there is a basis of, we have chosen a basis in which the density matrix is given by this form. Let's say n by n matrix. Its trace has to be 1, so the normalization should be 1 over n. All the others are 0. And let's compare it with row 2, which in a suitable basis can be written in this form. We know that row 1 is a mixed ensemble. Row 2 is a pure ensemble. Meaning that to describe the particles described by this density matrix row 2, we can just choose one ket. But in the case of the system described by the density matrix row 1, we cannot choose a single ket to describe them. Some of them will be described, some of the particles in that ensemble will be described by one ket, some of them will be described by some other ket, some of them will be described by even a third ket, etc. So in a sense, if our system is described by row 1, we have absolutely no idea what the ket of my system is. But if the system is described by row 2, then we know what the ket of. We know that the particles are described by a particular ket. We know it their ket definitely. So in a sense, for row 1, we kind of don't know anything about the particles. For row 2, we know everything about the particles. We know their ket. Now, how can we distinguish these two systems? So that's kind of the question we will ask. In the sense that, okay, so we said that there is a basis in which the density matrix looks simple. What if the density matrix is not given in this basis? So we already know that, for example, if you take the rho squared and calculate the trace of rho squared, if it is 1, it's a pure state, pure ensemble. If it is less than 1, the trace of rho squared is a mixed ensemble. But then still there is the question, how mixed? How can we quantify the mixedness, let's say? Now let's look at this quantity. Let me call it. Let me call it S minus the trace of rho logarithm of rho. So what this is. Let's calculate this quantity for both row 1 and row 2. Let me put a tilde over here. S tilde 1 is equal to minus the trace of row 1 logarithm of row 1. Well, the logarithm of a matrix in general will be complicated, but we can just use we can choose a basis in which it is diagonal. So this will be equal to minus, in the diagonal basis, sum over k row 1 kk logarithm of row 1 kk. Well, the diagonal elements of row 1, they are all 1 over n. So S1 tilde is minus sum over k 1 over n times logarithm of 1 over n. This is equal to minus 1 over n logarithm times minus logarithm of n. But they are independent of k. All the diagonal elements are the same. I still have the summation over k. K can take n different values because I'm talking about an n by n matrix multiplied by n. This is equal to logarithm of n. Does it look familiar? Well, if n is the number of states that my system can be in, logarithm of n is just the logarithm of the number of states that my particle can be in. They are all equally probable. So this is just like the microcanonical ensemble that you have studied in thermodynamics. And S tilde is nothing but the entropy, in a sense. Well, let's look at the other one for rho 2. Well, I can just do the same thing, minus the trace of rho 2, logarithm of rho 2. In the diagonal basis, this is rho 2 kk, logarithm of rho 2 kk. Well, only for one element this is non-zero. And for that element, rho 2 kk is 1. But logarithm of 1 is 0. So this is 0. So in a sense, this quantity, that we call S2, just measures our ignorance about the state of the particles making my system. S is usually in quantum statistical physics, S is defined as minus the Boltzmann constant trace of rho times logarithm of rho in terms of the density matrix. This is the entropy of the system. Well, let's see. Now this is an operator, so we can just basically use any basis that we like to write the rho. So let's use the energy basis. So what do we know? We know that any physical system, the second law of thermodynamics says that the entropy is maximized for any system. So kind of, now my question is, in the energy basis, what is the density matrix? That's the question I'm asking. Now, of course, to find rho, we are in the, let's say, we are looking equilibrium systems. So in equilibrium, the density matrix is not changing with time. So if it's not changing with time, it just means that H and rho, they commute. So I can diagonalize them at the same time. Rho will be a diagonal matrix in the energy basis. Rho 1, where the eigenvalues can be, well, let's say rho 1, rho 2, and rho 3, etc. Rho n. It's a diagonal system in the energy basis. So what should these rho i's be so that the entropy is maximized? Well, let's look at the microcanonical ensemble. What do we know? That rho, well, rho is diagonal, that is one thing. S, this is what we should maximize, minus the trace of rho, logarithm of rho, which is minus sum over k, rho k, logarithm of rho k. So we should find the numbers rho that will maximize this quantity with the constraint that sum over k, rho k is equal to 1. This is our constraint. And that's basically the only constraint we have. Well, this is a maximization problem with a given constraint, so the way you usually do it is just use some Lagrange multiplier. So I will just look at the variation of S plus mu sum over k rho k and I will just set this equal to 0. For rho k's that maximizes this value. Well, this is the variation of S is minus sum over k, rho k, logarithm of rho k, plus mu times sum over k, rho k. This should be equal to 0. Well, let me write this condition. This is sum over k, let me just take it out, minus the variation of rho k, logarithm of rho k, minus rho k times the variation of the logarithm of rho k is variation of rho k divided by rho k, plus mu times the variation of rho k. This should be equal to 0 for all variations of rho k, sufficiently small. Yes, we are looking at an extremum. We are looking at the maximum. So a very small variation of rho k shouldn't really change its value. So that's what we are writing here. It's flat at the top. It should be flat at the top. Now that tells me that the variation of rho k multiplied by minus the logarithm of rho k minus 1 plus mu should be equal to 0. But this tells me that for all variations, minus the logarithm of rho k minus 1 plus mu should be 0. Logarithm of rho k should be mu minus 1. Well, the interesting thing is constant, which tells me that rho k is a constant, and from the normalization condition we know that that constant has to be 1 over n. So that is our microcanonical ensemble. Well, let's look at the canonical ensemble. Well, okay, of course here just keep in mind rho k is a constant. But that constant can also be 0 or 1 over n. N being the number of particles that have the number of states that have the given energy. Energy is fixed in the microcanonical ensemble. In the canonical ensemble, well, these conditions we already have. But there's one more constraint. The average energy. Let's say the average of H, which can be written as sum over K, rho K, Ek. This should be equal to, let's call it U. This is the additional constraint we have. Not just one, but two constraints. In the canonical ensemble, we do let the energy fluctuate. It doesn't have a fixed value, but we ask its average to be constant. Well, we will basically do the same thing. We will look at the variation of S plus mu times sum over K rho K plus beta times sum over K rho K times Ek. Beta and mu are two Lagrange multipliers, and we should just set this to equal to 0. Solve for rho k and find the value of mu and beta such that they satisfy our constraints. So we have two constraints here. So we have two unknowns with mu and beta. They will be just chosen to satisfy our constraints. Well, let's write down this variation. Well, this up to this point, everything is the same. But to this one, we should also add beta times k variation of rho k ek. This should be equal to 0. Now you see the first two terms there are identical as before, so I just copied the result we had before. Now this tells me that minus the logarithm of rho k minus 1 plus mu plus beta times ek, this should be equal to 0. Logarithm of rho k should be equal to minus beta ek plus beta ek plus mu minus 1, or rho k is equal to e to power beta ek divided by some normalization. Mu and 1, they are just constant. Let's call that z. And beta, in statistical physics, you identify it with minus 1 over the Boltzmann constant times the temperature. And this z is nothing but sum over k e to power minus ek over k beta times t. But this is nothing but sum over k e to power minus h over kb times t. K, this is the definition of the Hamiltonian operator. But this is also the definition of the trace. This is my z. So you can basically build all your statistical physics starting from this density matrix. Any questions? Let's do one more example before we complete our density matrix. Now let's look at this. We had this. Let's consider a density matrix given by this combination. Minus. SMX ensemble. And let's calculate the averages of Sx, Sy, Sz. Is this polarized, unpolarized, under which conditions will it be polarized, etc. The average of Sz. This is the trace of Sz times rho. This is the trace of, if you add with Sz on rho, you would get omega plus h power over 2 plus omega minus h power over 2 minus. This is equal to trace of, let's say, h power over 2 omega plus trace of plus minus h power over 2 omega minus trace of minus. These traces are nothing but, in a sense, that you just exchange the order of the brackets in your operator. H power over 2 omega plus minus h power over 2 omega minus Well, these are just normalized to 1. So this is average of Sz is h power over 2 omega plus minus omega minus. In this step, well, you see, in general, if you have trace of alpha beta, well, you just choose a basis, an orthonormal basis. In that orthonormal basis, this definition of the trace is k alpha beta k. This is the definition of the trace. This is equal to sum over k beta k k alpha. This is equal to beta, sum over k, k alpha, but this is just 1, the identity operator. So this is equal trace of alpha beta will be equal to beta alpha in general, whatever the case beta and alpha are. So that is what I use. So this is our average S set. So if omega plus and omega minus, they are not equal, this system has a definite polarization in the plus direction, in the S set direction. It's not polarized in the x or the y. Let's look at Sx. This is equal to trace of Sx acting on rho. This is equal to trace of rho is omega plus, plus, plus. Sx is over here plus omega minus. Sx minus minus. And trace of Sx acting on the plus ket will be minus h bar over 2 minus plus omega minus Sx acting on the minus ket h bar over 2 plus. This is equal to h bar over 2 omega plus plus minus plus h bar over 2 omega minus minus plus, and this is 0. There is no polarization in the x direction. Yeah, this is not really a surprise because we are talking about the collection of particles which are polarized either in the plus z direction or in the minus z direction. And whether it's polarized in the plus z direction or in the minus z direction, the average of Sx will be 0. So in our mixed ensemble, the average will also be 0. Well, you see, you can just remember the action of Sx on the plus and minus if you remember the matrix representation. So Sx multiplying 1, 0 will be just h bar over 2, 0, 1. And Sx multiplying 0, 1 will be h bar over 2, 1, 0. Now, any other questions on density matrix? When rho is Hermitian by construction, you see rho, we had defined it as omega I, psi I, psi I. If you take rho dagger, this is omega I dagger, complex conjugate, times, I'll change the order, take the dagger of each one, but omega i's, they are nothing but classical probabilities, in a sense. So they are real numbers. Omega I, this dagger is psi I, the other dagger is psi I, which is nothing but rho. So rho dagger is equal to rho. Probabilities. How many of them are in one state, how many of them are in the other state, in a sense.
Ama işte burada kafam karışıyor. Probability'leri veriyorsa o zaman sadece bir function eklemiş. State'in bu kadar da...
You see, let's go back to the example at the beginning of the class. You see, when you are preparing it, you already know with which fractions you are mixing these things. The eigenvalues of rho gives you those fractions. For example, you were asking, how do you know the density matrix rho? Well, that's the question of statistical physics, for example. That's basically what the question you are asking for. I mean, what is the density matrix for a macroscopic system in thermal equilibrium? When you say that, okay, my system is in thermal equilibrium, it's in the, it has a definite temperature, which is just another way of saying that there's an average energy of my system. And I don't know anything else about my system. That's the only thing things I know. In that case, then the second law of thermodynamics combined with these definitions tell me what the rho should be. Or rho is basically 1 over z e to the power minus h over kBt. But for a particular case, particular system, finding rho is itself and on its own subject, own study, let's say. So the question is, how do you prepare the system? Because that will determine what your density of states is. Is it in contact with a heat bath? Then this is your density of states. Is it isolated? In thermal equilibrium, at least, this will be your density matrix. This one. Do you create it by sending it through a Stern-Gerlach apparatus and blocking one of the beams? That tells you what your density of states is. Or do you create it with a laser? Are you talking about some system of photons? Then depending on how you create, you have the corresponding density of states. The laser will be more or less a pure state, because by definition they are coherent. They are all in the same state, all the photons. But the light from the sun will not be in a pure state. It's just a mixture of all the kinds of polarizations. Okay, let's give a break. Then we will continue with angular momentum once more after the break.